I'm Rob MacNeill. I'm going to be talking on the same topic, but focused more on complex nonlinear FE for concrete structures. Just a quick slide about me. I'm a mechanical engineer by training, so I might be a little bit out of my element with a bunch of civil structurals here. So no tomato throwing, but I've mostly been in practicing in the area of applications of nonlinear dynamic finite element analysis for the past certainly 25 years, mostly with the program LS-DYNA, which is an explicit solver. I have done lots of different things, including impact, blast, failure analysis, investigations, all sorts of things with that. Usually high energy, fast sort of things. I have specialized expertise in transportation safety, especially with rail vehicle design, rail infrastructure, crashworthiness applications, and a bit of a niche area of aircraft impact assessments against structures. And on top of that, I've done a lot of testing, either in support of FE, trying to validate against modeling, or independent modeling, and a lot of it has been focused around, like full-scale train car impacts or blast testing, things like that, but down to, fundamental material response as well. So that's a bit about me. My outline is broken into 3 different areas. One, I want to step back, like what are the best practices before we start, before we really dig in and decide we need a complex approach. And then assuming we've decided that, what do we do best practice-wise about establishing a good methodology? So I'll talk about that, and I'll be stressing building up from basics, kind of following on what Paul said. Start simple before you go complex. That's my methodology, and I'll dig in there. And then I have a case study that hopefully will show the various steps that I'm preaching here related to an aircraft impact assessment for a nuclear power plant structure. So getting into before you start. Consider what the model needs to do. I think, again, this follows on. We'll see some common themes between our 4 talks, I think. I always think, will hand calcs or simplified methods suffice to get us the answer we need? Do we even need to do FE? Sometimes no, and if we can get away with more efficient methods, that's great. Say we're at a level of fidelity where we just need to ensure something meets requirements. It's doesn't have to be a super precise answer, and we can make some simplifying assumptions along the way. That's sort of a mid-level. And then say we really need a detailed, precise answer, within some percentage of a test response that we're going to go, or it's a critical thing. We really need to have a detailed, precise answer. So that requires a well-characterized methodology, and it takes the most time. It's the most complex. So, just kind of considering what level of fidelity we need to get into before we start. Continuing on, the elements of what we're modeling, we should consider at what complexity do we have to model them. Say if it's concrete, do we need to model the aggregate and the paste? Are we at that level? That's extreme. Normal detail that I get into is, say, a solid continuum of concrete with explicit treatment of the rebar, so individual beam elements within solids. I'll get into that level of detail pretty frequently. Oftentimes we can smear properties into a combined composite of concrete and reinforcing steel, and it can be a smeared continuum of solids, could even be a shell element based model. we should think about what kind of effects we need to have our model produce. Say in concrete, we want to model the damage, we want to model the cracking. We need to be able to predict how much spalling we'll get. This is important in nuclear power plant aircraft impact, for example. In steel, are we expecting to go plastic? So modeling the strain hardening, maybe out to necking and failure is important. Maybe we need to model the bond failure that might occur between the reinforcement and the concrete. It might be like an aircraft impact, it might be high strain rate, and we'll have to account for that in our material properties. And just before I get into it, explaining what we're seeing here, this was an investigation that I worked on trying to figure out why some precast reinforced concrete facade panels fell off a building, and I created some models around that. In this example, I knew a priori what the response was. That's an advantage. Oftentimes we don't know that, but still the methodology and the building up from simple to complex applied in this as well, where, as I show, kind of segueing into here, starting simple, establishing the methodology, building up from basics, start simple, and work your way into the practical example that we're trying to solve. If at the start I don't know how a material model behaves, I've never used it before, or I don't know how that finite element works, I'll do single element tests and I'll stress it in ways that I intend to stress it in my application. So I know from one element how it's going to react. And then replicating or calibrating material response is super critical. I'll approach this with replicating material tests. Maybe I have confined or unconfined compression cylinder tests or split tensile tests for concrete, or I have tensile tests from the steel. I will physically go replicate those tests in the finite element analysis with similar mesh density that I intend to use on my larger model to make sure everything is working out. That's the calibration step. So if there's anything, trying to figure out what could be calibrated, it's in that stage. And then, once I have the material properties, our material models well calibrated, then if necessary, I'll go into an intermediate step where this is a case where I can't test the ultimate goal, like an aircraft impacting a building. I need to go to an intermediate step where there's been representative tests done. I can model those tests, sort of testing system level behaviors and checking against those responses. And then, once that methodology is established, I can apply it to the larger scale problem that I can't test against. Continuing on with establishing methodology, an important step is choosing appropriate constitutive models or material models. Not all are created equal. I don't know if there's any LS Dining users, but there's over 200 material models that are available. You have to go in and understand what they do, and maybe that goes back to the single element tests to really test them out. But researching them, make sure they're appropriate for what we want to do with them. But generally, concrete, I'm looking in the geomaterial-based material models within the solver. For steel, it's typically, like a plastic hardening model. And they should be right-sized for the application. We're talking about nonlinear here, so more often than not, we're not looking at the elastic models, though they might be incorporated in places where we can use those. If cyclic response is needed, Not all concrete models will do cyclic response appropriately. That's a very important thing to look at. If we need to look at damage, cracking, failure, we need to understand how that's implemented in our models. Maybe there's thermal effects. Can the material model support that, or can it be added on? I mentioned rate effects. And here, I mean, people know concrete. We know that it's highly nonlinear. It's dependent on lots of things, including level of confinement. So those are things I think about when I'm establishing a methodology. And moving into my case study, the illustrations just show the different steps, sort of like from small scale, medium scale, full scale, global model. This case study, establishing methodologies for aircraft impact analysis on nuclear power plants. It's a mandated load case for all North American nuclear power structures that we do this kind of beyond design basis assessment for reactor buildings and spent fuel buildings. Historically, you know, back a ways, since they've been developing these have been done with hand calculations. I'd say within the past 20 or more, 25 years, we've been relying more and more on finite element analysis to help with these assessments and get more detail. But we can still use those hand calculations to check our work and sanity check. We're not going to do a full-scale test. We're not going to run an aircraft into the building to check our results. So we have to build up our methodology to have some faith in it. It starts with like the element tests, material calibration, starting with concrete. As I mentioned, it's complicated and very multivariable. Can depend on the loading environment, and that all needs to be accounted for. There's different models that I tend to use. Some have empirical data in it that you could supply, pretty basic inputs, and it will extrapolate to different conditions. Sometimes that's okay. Oftentimes it's not. Always have to understand the shortcomings and what goes into what empirical model is in there that it's extrapolating from. And then as needed, if we need more and more precision, we'll have to get in there and specify all of the 100 parameters that a concrete model needs, and we'll have to look at we'll have to have test data to characterize that concrete at different confining pressures, for example. And this kind of goes on from that, but different response from unconfined versus confined pressures. This is some data. I'll get into it. These are from characterized tests from this IRIS 2010 experiment that I'll show in a couple minutes that I use to help validate the model. For steel, it's a lot more straightforward than concrete, but still, steps are needed. We need true stress, true strain, for example. The tests that we get from uniaxial tension tests are always an engineering stress strain. We need to do conversions and calibrate, do first order corrections and maybe second order corrections if we want to go past necking and out to failure, implement appropriate damage models, etc. And this is just showing a calibration exercise that I did this was for a A490 bolt, but it's the same for any sort of steel and a lot of other metallics. Strain rate effects can be pretty important. I think in concrete especially, there's kind of I think this is where experience comes in at very high rates. It's more of an inertial effect, and you don't actually put the dynamic impact factors on top of what the strength already is, it's an inertial effect. It's like a confining, localized confining pressure kind of response. So if you hit it really fast, locally it confines, and that's where your dynamic impact factor comes from. You don't need to add these. For steel, it's different. You do need to add strain rate dependent models. And you can see, that was from some research I did a while ago trying to characterize a class of rebar. It can be all over the place, and that defined the bounds of uncertainty for this problem. I don't know with precision what I'm trying to model in all cases. So understanding the bounds of what I know, how precise I know it, is important. So moving into benchmarking against appropriate experiments, for this application, I've done a lot of work validating my methodology that I built up over time against these iris experiments that I mentioned. And there are a series of impact tests against reinforced concrete panels. It was designed to inform the industry and modelers like me to establish good methodologies for these. And so it was well characterized, very highly instrumented, all the materials, cores were taken, lots of data to help our methodology development. And it was impacted with flexure and puncture response done independently. This is kind of showing the test setup. It's a gas gun that sends a missile against a concrete panel. They were roughly 6 by 6 by maybe 5 or 6 inches thick. Just kind of showing a high-speed still of a missile impacting, and then the kind of scabbing pattern that you see on the backside for a puncture test. This is the test frame. The schematic kind of shows what the test frame was built to, and the rest are the model that I developed to replicate the test frame. I threw a lot of detail at the test frame to try and minimize uncertainty. So I don't want to make assumptions about boundary conditions, so I put in more explicit detail so I don't have to justify or wonder what the effect of my assumptions were. So again, I mentioned these were highly instrumented. There were strain gauges on the faces. Rebars were strain gauged internally as they were cast. There were displacement like LVDTs. There were load cells on the back of the frame. All of that detail I incorporated into the model so I could pull it out directly and compare to measured response. And just to give you more feel, it's a fairly heavily reinforced concrete panel. The panel I modeled with solid elements, beams for the rebar that were embedded. There's some steel angles around to interface with the test frame. The missiles themselves, which I modeled in detail, the puncture test, it was basically just a concrete-filled steel case. So it was big and heavy, creates a hole. The other one was a hollow steel tube that was designed to buckle and induce just a flexural response, not a puncture response. But I modeled the missile so it buckled appropriately and even validated against that. And I can't show too much of the comparisons that I did, but this gives a feel for some of the metrics we could pull out. Some of the comparisons are qualitative. We're just looking at crack patterns and how things broke up. But there was a lot of qualitative as well that we could judge against. I'll mention that I mentioned uncertainties. Even though it was well characterized, there's still a lot of uncertainties around this, and many variables with uncertainties. When I'm thinking about scaling this up to the global aircraft impact, trying to understand the response with all of those uncertainties becomes unwieldy. So what I did here was I did a design of experiments parameter screening study to try and determine which of the many variables that we had were actually important. And so we can reduce the number of variables down to, say, from 50 to 10. And we study the response in our range of uncertainty for those 10. And we look at bounding the response. Does our understanding of those important parameters within our range of uncertainty, does it bound the response? And we got to a point where it did, and we could come up with a baseline to carry into our global model. So carrying that established methodology plus other things, like for this, we use industry accepted practice out of NEI 713 to guide some of the inputs. Again, we still rely on hand calculations to do sanity checks. In nonlinear explicit calculations, there's other things we do commonly. We check calculation energies. Are we gaining or losing energies? Are there things like hourglass energies, if you're familiar with that? Is that out of control? Is our time stepping appropriate? Things like that. We check the reactions. Do they match the inputs? And then we apply intuition. Does it look reasonable? For this, the load is an aircraft impacting the structure. There's different ways to do this. I've done it from very detailed aircraft models impacting structures to this kind of approach, which is called a modified Riera approach, where we are applying the load separated in space and time and developing these curves that are shown, force versus time, by slicing the model axially along its length and apportioning the mass in different buckets for like the engines, the wings, fuselage, and using F equals ma kind of inertial change in momentum kind of calculations to come up with the forcing functions. And then this is the global model. Again, kind of adding on to what Paul was saying. First we look at, does it look right under gravity loads or under simple loading? And that's what's shown over here. So an initialized model with displacement contours is shown. This is for a reactor building where it's a double-walled structure, a very heavy outer structure that is designed to take most of the aircraft impact. And then the inner containment, which is cylindrical with a spherical dome on top. Hopefully, that's never engaged, but this is all very heavy-duty reinforced concrete. There's even a steel liner on the inside of the containment building to catch any scabbing products. The inner container even has pre-stressing tendons to put it largely into compression when initialized. And so we go through all of those steps before we add our insult on it. And then the middle shows the footprint of the aircraft that I put on it, and then use those patches to apply those load history profiles. And then over on the right shows post-impact response. The one on the right shows a case where we were impacting it close to the top corner of the outer containment. And you can see, the displacement of the outer containment is substantially larger than the inner containment. We also did things like captured the shock response spectra and put those on localized models of equipment on the inside. So that kind of shows the process from basics all the way up to this global model that we can't validate in reality, but it's validated by stepwise. So yeah, in summary, start with your planning. Consider what you need your model to do. Do this V&V at all stages as you can in building up your your modeling methodology. Start simple and build the complexity. Characterizing fundamental material response is so key. That's really where it starts. And then, you know, as much as you can compare to other adjacent testing opportunities, or if you know the answer a priori, like the earlier one that I showed, that's a good thing to compare against as well. So that kind of concludes that. But similar to Paul, you know, I'm curious to know if there's practitioners here that do this sort of modeling, if you have things to add, or I'll take any other questions.
Thank you very much. I really benefited from the benchmarking part because I see junior engineers, that's the most neglected area. You know, I see a junior engineer comes to me with a rather complicated FE model, nonlinear model. They are trying to figure out whether it's correct or not. And my question to them, have you modeled a simply supported beam? Have you got some good results before? Because, you know, if you haven't validated your modeling approach, let's say you are modeling a blast load analysis, the first step should be to model something with the known response. It could be an experimental specimen from literature. You can model it. You can confirm that what you are doing in terms of modeling boundary conditions, reinforcement, concrete, etc. So I think that is a generally neglected step or omitted step. Engineers have a tendency to go into something really complicated and try to use all complex modeling approaches and then hope to get it right or hope to justify it. So for that reason, those like discrete, simple analysis, I think there's a tremendous value of doing this before anything else.
Thanks for that comment. Yeah, and this is just one example of a benchmarking exercise of many that I've done throughout my career. Yeah, if you're doing something that's trying to do something that's complicated, go to the literature, look for similar experiments or closed form solutions, things like that that you can validate your methods against. Thanks.
Thanks, Rob, for the great presentation. This is Isa Rahmani with WJE. You talked about calibration of the material properties using some test data, which is great, but a lot of times when you're especially dealing with existing structures, you don't have the luxury of having those tests available, you know, to do the calibration. What is your go-to approach when dealing with those types of questions?
Yeah. So for concrete, it's, you know, normally during construction you will have had cores or samples prepared on the side. You'll at least know the unconfined compression strength, and you'll know the density. Those are key inputs. And then it comes down to an evaluation of what's the stress field for this really look like? Are you going to have high confinement? You know, maybe just using the conservative assumption that, or having conservative confinement assumptions is all you can do. Again, it's kind of down to the problem, try and have conservative approaches, and understand your level of uncertainty. Steel is a lot easier, but the concrete is the hard part. Thanks, everybody.